Hello to my Algebra 2 students. Welcome to this little video that's going to review some of the topics that we talked about in topic 1 in preparation for your first test of the year. So just as a heads up, the lessons that we're going to be taking a look at in this video are the ones you see on the screen here. So those are key features of functions, transformations of functions, piecewise functions, arithmetic sequences, quadratic and absolute value inequalities, and linear systems. All right. For those of you that came by and picked up one of those review worksheets from me, you're going to want to follow along as I work out the problems you see on that sheet here on the screen. But you might also want to have a separate sheet of notebook paper with you. You can also do this in your notebook and title it Topic 1 Review, just so that you have somewhere nice and neat to keep all of the work that we're doing for these problems. Now, because some of these are based on graphs, I will be doing them on the worksheet itself, and I'll be putting all the answers on the worksheet. But having a separate sheet of notebook paper will be nice just to make sure you have all of the reasoning and working in some place. All right, so we're going to go ahead and get into it. And I'm going to start by taking a look at numbers 1 through 5, all right? So we're given this absolute value graph, and we're asked to write all our answers and notations or interval notation for this function's key features, all right? I'm gonna go ahead and get my pens out. And so the first question they ask us is, what is the range of this function? All right, so if I'm talking range, I'm talking about where this graph's lowest point, so I'll mark that here, and where the graph's highest points are. And because this is a positive absolute value function, what we should recognize is the top of its range, its highest points, are going to be infinite. And we can tell because of those arrowheads on either side of our graph. Now, as for the bottom portion, these absolute value functions don't decrease forever. And so we see it has a minimum right here at this point at -4 on the y-axis. And so that's going to be what we put. All right. So this graph starts at -4 on the y-axis and it ends increasing, going upwards never. All right. Now, number 2 asks, what is the domain for this function? And so instead of thinking about this in terms of high-low, now we're thinking about it in terms of left-right. And again, we're looking to these arrowheads to kind of make that decision for us. We see this graph is going to continue left forever, and it's going to progress to the right forever, right? So those arrowheads indicate to us that the domain for this function, and this is true of all absolute value functions, is going to be all real numbers from -infinity to positive infinity. Okay, so its range is finite, at least on the bottom end. It goes to -4 and goes up to infinity. But for the domain, that's infinite. Again, that's true for all absolute value functions. Number 3 says, what is the interval over which h of x is increasing? So we're looking for where the graph is progressing up as we read it from left to right. And if we notice, that's not always true. If we track the movement of the graph over time, we see that it starts having this downward motion, and it keeps progressing downwards until it stops at that minimum we pointed out earlier here at -4. But now we're going to talk about that in terms of its x value, so that is at 3 on the x-axis. And once the graph hits 3 on the x-axis, we see that it starts to progress upwards. And it continues to do that based on what this arrowhead tells us towards infinity. All right. So if we're going to answer where the graph is increasing over what interval, we're going to say it's increasing from where x is 3 to where x is infinity, or approaches infinity. Number 4 says, over what interval is g of x, supposed to say h of x, negative. Okay. And so now we're looking for all the places where our graph is negative, that means below the x-axis. And so I can see that's this chunk of the graph starting right here, right? Everywhere down below here is that negative portion of the graph. It's below the x-axis. And I can see that starts here at 1 on the x-axis. The graph progresses down, hits -4, that minimum, and then rebounds back up until we hit here 5 on the x-axis. And from there, the graph continues upwards positively. So we're going to answer that question. Where is the graph negative? It's negative from 1 to 5. And the last one says, what is the value of the y-intercept for g of x? Again, that's supposed to say h of x. And so we can see that being true. If we're looking for the y-intercept, we're looking for the place where this graph crosses the y-axis. There's only one place that happens, and that is right here, where our y value is 2. So we're going to write 2 for that. So those are some of this absolute value function's key features. Let us move on to number 6. Number 6 says the graph of y is equal to x minus 1, and then we're getting the absolute value of x minus 1 plus 7 is reflected across the y-axis and then translated up 1 unit. They're asking us, what is an equation of the transformed function? So we're taking this one that we're given. I'll highlight it. Y equals the absolute value of x minus 1 plus 7. We're reflecting it across the y-axis, and then we're translating it up 1 unit. So let me start by just sketching a rough graph of this function, and I'll do that over here to the left. This is where that notebook paper is going to come in handy. And so I'll label this number 6. And so if for number 6, again, they're giving us this function, absolute value of x minus 1 plus 7. We can compare that to the base parent function or standard function for an absolute value, which looks like this. A x minus h plus k, right? Where h comma k is the vertex. Okay? And so if we're looking at this graph, again, I'll sketch it really quickly. We don't need a super detailed graph, but it's going to look something like this. We're going to have our graph looking like so. And so our vertex is going to be, at that point, 1, 7. You'll notice that that minus is in front of the 1, just as it is in the h in our base function. And so we're going to kind of ignore it, right? If we see minus 1, we should recognize our vertex is at positive 1. So put a positive 1 on the x-axis. And we're going to put a positive 7 because we see the plus is also there in the base function. So we'll put a place at 7. All right? And so our vertex is there for this function. And because our a value is positive, we see no number, no a value in front of the absolute value, so we assume there's a 1 there. Because our a value is positive, what we can tell is our graph is going to progress infinitely from that vertex, so it looks like this. Last one was bad. Let's go back and fix that. So something like that, right? All right. And so we're looking for the reflection, or rather the transformation of that function from the ones that we've seen. All right, so they say it's reflected across the y-axis. And so that should point out to us that we're eliminating A and C as answer choices. All right, because both of those contain this negative that would reflect our graph across the x-axis. That is to say, and I'll go back to the graph we drew, instead of going up like our function, our sketch does, those would go down. Okay? So because that does not work for us, we're going to go ahead and we're going to say that A and C are not answer choices. That makes sense for us. Which leaves us with two options, B and D. All right? Now, between the two, what we notice is that they have the same x value for the vertex, And that x value, if you're paying attention and looking at the minus we have there, the x value in 6 for B and D, they both say positive 1. Let's take a look at why that would be considered a reflection across the x-axis. If we're looking at the x value -1, what that's doing for our graph is it's taking its vertex, I'll use a different color here, I'll use green, and it's putting it over here instead of right there on the right, okay? So both of those counts as reflection over the y-axis. The question is, which one performs the other transformation we're looking for, which is what we see here, that translation of 1 unit up. And so for our function, we see that its vertex sits at 7. The answer choices we're given have a vertex that sits at 6 and a vertex that sits at 8. Now we know, because of, again, that little comparison we made earlier, if we're looking for a translation up, that means our function should not sit at 7. Instead, it should sit up here at 8, which means our graph would end up looking something like this. Okay? And if that's true, the only equation of the lot that would give us that graph is D. So all the answer choices are eliminated except for D. That'd be our final selection there. Okay? We're going to move on to number 7. So number 7 asks us, over what interval is the graph of y equals x minus 2 squared decreasing? And so we're going to do another little practice in sketching our graphs. Okay. So they give us this equation. I'll look at it again. X minus 2 squared. Y equals x minus 2 squared. And they're asking us, over what interval is this decreasing? So let's picture this, right? We have this graph, and if we want to make it closer to its standard form for a quadratic, one thing we can do is we can go ahead and we can put that plus 0 on the outside. Now it looks like that standard form, which are right below. Y equals a x minus h squared plus k. Very similar to the absolute value function we just looked at, where again, h comma k equals the vertex. And so from that, we should tell that our function sits nicely on our x-axis at that point 2 on the x-axis and 0 on the y-axis, so it sits on the x-axis directly. I'll draw this one in blue. And nothing too fancy is going on with it. It's just going to progress upwards because its a value is positive. Okay? So if they're asking for where this function is decreasing over time, we're looking for the place where if we read the graph from left to right, the graph is going downwards. And we see that's happening. Oop, let me not use that then. That was not super visible for us. We see that's happening all along this portion of the graph right here, right? This portion of the graph is where, if we're reading from left all the way down to the vertex, the graph is decreasing over time. So we get that downward movement along this portion of the graph before it rebounds off of the x-axis and then pops back up, right? And so how would we describe that? What we would say is it starts decreasing from this little point right here, which we call the left end of the graph, right? And that's that arrowhead, which tells us it starts decreasing at negative infinity. Okay, use scare quotes there because starting from negative infinity is kind of a weird concept. But it's going to start decreasing from negative infinity, and it's going to continue decreasing all the way until we get to that vertex, which is that point there at 2 on the x-axis. Now, Savis is a little inconsistent about this, but we know we should have some kind of bracket there to indicate that our graph actually does touch 2. On Savvis, it seems to be the case that what they want you to write is just with brackets, or with parentheses rather. So negative infinity to 2 in interval notation. Okay? And so if that's true, then our answer would be B. Number 8 says, identify the translations of the parent function f of x equals the absolute value of x that give g of x equals 2 plus absolute value of x plus 3. So they may be trying to trick you here, but really and truly, this one's pretty straightforward as long as you remember what an absolute value function looks like by default before we plug in any numbers for it. And so we can think of it like that vertex form for a quadratic. We know it should look something like this. And I'll go ahead and write this on the side. No need to squish it in there. So we know that a quadratic, or rather absolute value by default, looks like this. No squared, this is absolute value. Let me get rid of that. All right. And now the function they've given us looks like this. Right? And the one we started with looked like this. All right. So all we have to do to figure out what's going on here in terms of transformations is compare what we see here to what the original function gave us. And the two things you should recognize are this plus 2 being added on to the entire absolute value function, and this plus 3 that's getting added on to the x value. Okay? So when we compare that to what's happening in our base function where there's nothing being added on, we got to look at what that number inside the h value does for the vertex. And the reality is that's going to move our graph left to right. And that's going to function opposite to what you would expect. So if you see plus 3, what you should recognize is there should be a minus there by default. And so what you're actually seeing is a little closer to this. Okay? That plus 3 is the result of having a double negative. That's minus 3. Okay? And if we see a minus 3 there, what we should tell about that is that the first transformation we see is a shift 3 units left. Okay? So transformation number 1 is a shift of 3 units left. Now what do we do about this 2 that's being added onto the outside? We'll go ahead and rewrite it back in. Let's add it onto the back. That 2 is in the same place that our k typically is. And remember, that controls the vertical position of our vertex. That is a vertical shift, okay? And so if we see that vertical shift of plus 2, we go ahead and we trust the sign of the number attached to it. We see plus 2, that is a shift 2 units up. So the difference between where we started and where this new function takes us is those two transformations. We shift left 3 units, and then we shift up 2 units, which means that we are selecting answer choice C. Up 2 units, left 3 units. 9 here deals with more transformations, but this one's even easier. It says the graphs of function g of x, which I'll circle in red here, and f of x, I'll circle in green, are shown where f of x is the parent function. So that's the original one, that's the base one, that's the one where we take whatever we're doing to it, apply it to it, and now it becomes g of x. They're asking us to complete the sentence, and so the sentence reads, the graph of g of x is the graph of f of x shifted blank 3 units. Okay? So if we look at f of x and g of x, we notice, and we can tell by looking at their vertexes specifically, that the major difference here that we see is this movement downwards, right? The vertex got dragged 1, 2, 3 units down. And so that's what we'd write. That's what we select. Shifted down 3 units. And that's as simple as that. And number 10 here is where things step up just a little bit in difficulty. We've got Keith, who's riding a bike at a constant speed and taking the same route to and from the park. His distance from the home, d in miles, x, minutes after he begins, is modeled by the function d of x is equal to negative 3 over 10 times the absolute value of x minus 10 plus 3. We have to figure out what the domain for this function is. And so we're going to go ahead and we're going to picture it again. As much as we can picture what these graphs look like, or what these functions look like as graphs, the easier a time we'll have with these questions of domain, range, key features, transformations, what have you. So I'm going to rewrite it here. It says d of x is equal to negative 3 over 10 times the absolute value of x minus 10 plus 3. And they ask us for the domain where x equals minutes and where d represents, I believe that said miles, but let's double check, distance from home. In miles. All right. So, if we are paying attention, we recognize, just like a bunch of the other examples, we have an absolute value function here in its quote-unquote vertex form, right? We're comparing it to those quadratics. And we see that it has an h value of 10. We ignore the negative because, again, that minus is already there in the default equation. So what we can take from that is this absolute value function has an axis of symmetry. We call that AOS of 10. Okay? And so here's why this is helpful. If we're considering x in this situation represents the number of minutes that he's been traveling to and from the park, we expect the start of the domain, the start of the x values for this relationship, this function, to be 0, right? As soon as he's leaving his home, he's at 0 minutes traveled. Let's show why that works out algebraically. So d of 0 is equal to negative 3 over 10 times the absolute value of 0 minus 10 plus 3. And let me go ahead and make 0 distinct color here so we can see it a little more clearly that that's where we're plugging in. All right. So let's go ahead and simplify. The absolute d of 0 is equal to negative 3 over 10. 0 minus 10 is negative 10. And so we have the absolute value of negative 10 plus 3. All right. The absolute value of negative 10 is just 10, right? Because negative 10 is 10 spaces away from 0 on the number line. So we're going to go ahead and rewrite that as negative 3 over 10 times 10 plus 3. Absolute value of negative 10 is 10, so that's why we're allowed to just take that number out of the absolute value bars. We're considering the definition of absolute value. And now we're going to finish simplifying by doing that multiplication. Negative 3 over 10 times 10 gets me negative 3, plus 3 gets me 0. So for our input here, we plugged in 0, we get out 0, and that makes sense, right? What this is saying is, after 0 minutes traveled, we're 0 minutes away from, or 0 miles away from home, right? And that tracks, we haven't left yet. So that would be the beginning value of our domain, 0, because that's a time when we're starting. So the question asks us, what's the beginning and what's the end? And so to think about that, I'm going to take you back to our axis of symmetry here. If we're picturing what this graph looks like in our head, we have this y value, or this y-axis, we have this x-axis. we know we're starting at 0, 0. That's the origin of the graph. And we're progressing in distance away from home until we get to our vertex, which we're saying, according to our key feature there, our vertex, according to the function, is at 10 on the x-axis and 3 on the y-axis. All right? 10 is the halfway point in this journey, right? So we're traveling, we start traveling for 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes, and at 10 minutes, we get to the park, right? And the reason we know that to be true is because this is the maximum distance that we travel away from home before we start to travel back. And so we've created this kind of absolute value function by paying attention to the key features in the scenario presented to us. So if this chunk right here is 0 to 10, right? That's 10 units. And we know that axis of symmetry splits this graph perfectly down the middle. Then what we have to recognize is from halfway until the end must be another 10 units, leaving us at an x value of 20. Okay? So my proposition is 20 is the end of our domain. After 20 minutes, we'll have reached back home. Let's see if we can prove that algebraically. So we're going to take the same equation. D of x is equal to negative 3 over 10 times the absolute value of, we're going to plug in 20. And so let's make the x here 20. Minus 10 plus 3. D of 20 is equal to negative 3 over 10. 20 minus 10 is 10. And we're going to consider the definition of absolute value here. The absolute value of 10 is 10. So again, we can just go ahead and make it a 10. Negative 3 over 10 times 10 is going to give us negative 3, which again, plus 3 gets us 0. So if we plug in 20 to this equation, we still get 0, which shows us, yeah, that is a sensible place to call the end of our domain. At 20 minutes, we're back at home. And so that should tell us then that our answer for this is a starting domain of 0, or start to our domain of 0, and the end of our domain is at 20. All right, on to number 11. Let's run the back side of that page now. For number 11, they tell us the graph of f of x equals x squared has an x-intercept of 0. They ask us, where will the x-intercept for h of x equals x plus 9 be located? So really and truly, a good trick for this one is, if we're comparing these two, they tell us we're looking at f of x equals x squared and f of x equals x plus 9 squared. Again, pay attention to what the vertex form for this top one would look like. So let me change that into what will look closer to the vertex form. F of x equals 1. And maybe I don't need to write the 1 because it's pretty evident that identity property tells us there is a 1 there. X plus 0 squared. Right? So that in red is the same thing as the one that we were given. And this in white is the new function they give us. If we are to compare the vertex for both of these, this one sits at 0 on the x-axis. We expect this one to sit either to the left or to the right of 0, 9 units. Now to figure out which one that is, we want to pay attention to the sign we're looking at here. And because we see a positive, and remembering that horizontal shifts are usually the opposite of what we expect them to be, if we see a +9 here, what that actually tells us is that the vertex for this function is at where x equals -9. So that plus sign indicates to us a vertical shift 9 units to the left. Okay, so our vertex is going to sit at where x equals -9. Number 12, we've got this function f of x that's graphed for us, and they tell us that it has a domain of -2 to 2. So these are hard stops. Okay? They ask, what is the domain of g of x if it is f of x, but we're multiplying the x value by 2? Okay? So what's happening there is we have this kind of horizontal compression happening. Because whatever x value we're plugging in, that number is being taken and it's getting jacked up by a factor of 2. And so what that means is, as we progress outwards from our vertex, the function is going to travel more quickly than it otherwise would. Because the x value that we're plugging in is getting multiplied by 2, right? So the graph moves quicker over time. And so while the original, the parent function, has the domain of -2 to 2, ours is going to have a domain that's closer to -1 to 1. And if it continued, you would see that it has a more narrow trajectory compared to the one they gave us, which is going to be traveling a little more slowly out from the vertex over time. Okay. Number 13. So number 13, we're going back into some more familiar territory. These are our systems of equations, and they want us to find a solution for this. We can find any number of ways to do this, but this system seems to be set up to most easily solve with substitution. And I say that because we see the first equation here is given to us with one of the variables x already solved for. So we're going to take that and we are going to use it to our advantage. It's number 13. And so that equation is x equals 2y minus 3. And the second equation is 4x minus y equals 16. All right. So like I said, we're going to take this value for x that we've been given. We've been told that x is equal to 2y minus 3. And we're going to substitute that for the x in the other equation. So this is what that's going to look like. 4, instead of x, we're going to write 2y minus 3 minus y is equal to 16. So now that we have that substitution taken care of, we've gotten rid of the situation where we have multiple variables in the same equation. And so if we solve this, we're going to end up with a number for an answer. So let's go ahead and simplify this first. We're going to distribute this 4. That's going to give us 8y minus 12. That minus y on the outside stays, equals 16. We're going to combine like terms, so 8y and negative y come together to get you 7y. And now we can solve this like normal. Adding 12 to both sides. Which leaves us with 7y equals 28. And then dividing everything by that 7. leaving us with y is equal to 4. So one part of our solution for this is that y equals 4. But remember that the solution to a system of equations is the place where the two lines of those equations cross. That's a point on a coordinate grid, and every point has an x and a y value. So to find the corresponding x value, we're just going to go ahead and we're going to plug that value for y we got back into one of the equations, and that one we worked with originally, the x one, seems to be the easiest. So let's just work with that. 2 times 4 is 8, and 8 minus 3 is going to get me 5. So that is the second portion of my solution. Now I'm finished, and I know this function has a solution, or these functions have a solution, a point of intersection, at where x is 5 and where y is 4. And so the answer for this one is D. Number 14 says we have to consider the system of inequalities, and it's going to be our job to select all the points that represent a viable solution. So there's a few different ways you could do this. The easiest to me is let's just go ahead and check each of these points they give us against all of these inequalities, and we can use two of these to make our lives a little easier right away, right? We see this last inequality here, y is greater than 3, gives us some opportunity to eliminate some possibilities. So our point is only going to count as a solution if its y value is greater than 3. That's true of A. B, it is not true of C, so C does not work. D works for an E. So we know C and E are out because their y values are 3 and 2, and we know our y value has to be greater than 3. We can also use the second inequality, y is less than x, to help us out. Any solution that has an x value that is greater than its y value, or a y value that is less than its s value, is going to work for us. So for that reason, A doesn't work, because its x value 5 is less than its y value 6. But the other two, B and D, are fair game. So we're going to have to check both B and D against our first inequality here, which says y is greater than or equal to 10 minus x. Number 14. So y is greater than or equal to 10 minus x. And the 2 points we're checking that for are, I believe it was 6, 5. And the other one was 9, 4. All right. So let's check these 2 points out to see which, if any of them, work. Okay? So for the first one, we're going to say our y value, which is 5, is greater than 10 minus x. Let's plug it in. Or equal to 10 minus our x value, which is 6. If we simplify, we end up with 5 is greater than or equal to 10 minus 6 is 4, which is a true statement, so that works. And so that solution does make sense. We're going to select that one because it made everything in our inequality system make it say something true. Let's go to the second one, which says 4 is greater than or equal to 10 minus our x, which is 9. If we simplify that, 4 is greater than or equal to 10 minus 9 is 1. That also works, so we would also pick that one. So our only remaining points both count as solutions to our system of inequalities. So our answers here are B and D. All right. 4 more problems and a few bonus ones just to make sure that you are fully prepared for your exam. 15 says, one equation in a system of equations with exactly infinitely many solutions is 2x plus 4y equals 10. They ask us to select all equations that could be the second equation in this system. Okay. So when we say we have a system with infinitely many solutions, what that means is the two or multiple equations in our system are identical or equivalent. Okay, so we could make them all into the same equation because the relationship between their inputs and outputs is identical. The equation that we're given here is 2x plus 4y equals 10. And so if we're looking for equations that have infinitely many solutions when compared to this one, all we're looking for is which equations could we make look exactly like this one. Okay? And so I'll give you an example of what that could look like or couldn't look like. Go over here. So the equation we have here again is 2x plus 4y equals 10. And then the next equation they give us is x plus 2y equals 5. So if you're paying particularly close attention to these two equations, what you should notice, hopefully, is that they are pretty similar. It's just that the bottom one is the top one divided by 2. Or you could think of it as the top one is the bottom one multiplied by 2. If I multiply everything in here by 2, x becomes 2x, y becomes 4y, and 5 becomes 10. And so what that means is both of these equations are equivalent because we can make them either divide out or multiply out to be the same equation. Okay? So these are equivalent equations. And if they're equivalent equations, if we were to graph them, we would have infinitely many solutions because, again, they're constantly overlapping. They're the same line. So we would pick that one. However, if we tried the same trick with the next equation, where the only difference is we have 2x plus 4y equals 10, and this next one is x plus 2y equals 3. If we tried the same multiplication trick, we'd end up with 2x plus 4y equals 6. And you see how these two are no longer the same. So B does not work as an answer choice. If we go to C, we're given 2x plus 4y equals 10, and the new equation is 2x plus 4y equals 9. Again, their results don't equal the same thing, so they cannot be the same equation because their coefficients are the same. So there's no way we could change that by multiplication to make it work. And so we're left with these two, 4x plus 8y equals 12. And 4x plus 8y equals 20. And again, comparing both of those to the original equation, we see something similar to what happened with the first set of equations we looked at. So between these two on the right, we see 2x, 4y, 10, we see 4x, 8y, 20. If we took everything in the top equation, we multiplied it by 2, we'd end up with what we see in the bottom equation, right? 2 times 2x. try that again. 2 times 2x gives us 4x. 2 times 4y gives us 8y. 2 times 10 gets us 20. So that shows again that those two are equivalent equations. That is good to go. But over here on the left, we don't see the same pattern, right? The coefficients are the same. So we try to multiply everything by 2, and that works for this and for this. But 2 times 10 does not give me 12. So that is a no-go. We would not pick that. So then our final answer choice is E. Okay. Number 16 asks us to solve each inequality. We have to write the solution in inequality notation. We're going to use every shortcut possible to us to make this as simple as possible. Let's go ahead and solve these quadratic and absolute value inequalities. First one says x squared minus 3x is less than 0, or 0 is greater than x squared minus 3x. Okay. Now to start this off, I'm going to go ahead and just use our reflexive property to flip this around, make this a little nicer to see. So instead of 0 is greater than, we're going to write this as x squared minus 3x is less than 0. If we're going to flip the statement around like that, we got to make sure that we flip the sign to indicate consistency in our relationship here. From here, we can go ahead and we can factor, right? So we're looking for all the... Actually, this is pretty simple factoring. We say x squared minus 3x. We can break this up into x and x minus 3. Less than 0. We can use our zero product property to say if we're multiplying these two things and we're getting 0, it's because one of them is 0. And so we can split this up into x is less than 0, and x minus 3 is less than 0. This tells us that one of our x-intercepts, our solutions, our roots, is 0. The other one, we're just going to do a quick bit of work, adding 3 to both sides. And that's going to show us that x is less than 3. So our second 0 is over there at 3 on the x-axis. Now we're going to use that little trick that we talked about in class, right? We're going to picture what this graph looks like. And so if we drew an x-axis with intercepts at 0 and at 3, we know this graph is going up because its a value is a 1. It's a positive 1. And so our function would look a little something like this. And we're being asked to find where on this graph are we less than 0, right? So if that's true, we wouldn't be looking to this graph's ends because those are the places where we are greater than 0, where the graph is positive. We're looking for everywhere in between. So that's all of this chunk of the graph right here. And so that's going to be between the zeros that we found. For this inequality, the solutions are going to be anywhere from 0 to 3. All right, anywhere in between is where this graph is going to be less than 0. Let's go ahead and write it. So anywhere from 0 to 3. For absolute value, let's go ahead and solve that. The absolute value of 2x plus 5 is less than or equal to 11. Absolute value of 2x plus 5 is less than or equal to 11. So when we have a situation like this, right, where the absolute value statement is by itself, we're going to go ahead, we're going to consider the definition of absolute value. We're going to consider the possibilities. If we're saying that what is in here, this chunk of information, has an absolute value that is less than or equal to 11, that means what's in there can be at most 11 spaces away from 0 on the number line. It could be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 spaces, but it is at most 11 spaces. And that's going to be true in one of two scenarios. Either 2x plus 5 is less than or equal to 11, or 2x plus 5 is greater than or equal to negative 11, right? In the left situation, what we're saying is our expression can have a value that is up to 11, right? It can't be greater than 11 because then there'd be more than 11 spaces away from 0 on the number line. And over on the right side, this expression has a value that is greater than or equal to negative 11. If it was less than negative 11, then it would be more than 11 spaces away from 0 on the number line. For example, negative 12 is more than 11 spaces away from 0. So let's go ahead and solve. And this should make quick work of what we're looking at here. To solve, we're going to go ahead and we're going to subtract 5 from both sides. And because the setup is the same, we're doing this in every one of these equations. We end up with 2x is less than or equal to 11 minus 5 is 6. Let's go ahead and divide both sides by 2. And we end up with x is greater than or equal to 3. Over here on the right, we do that simplifying. We get 2x is greater than or equal to negative 11 minus 5 is a negative 16. Then we divide both sides by 2, same as before. And now we end up with x is greater than or equal to negative 8. So x is less than or equal to 3, but greater than or equal to negative 8. We can write that out in the compound inequality. X is in between negative 8 and 3. Okay. Let's go ahead and write that down. Now we're almost done with me, so bear with me. Number 17 asks us to solve this system of equations, and this time we get the interesting combination of an absolute value, so a nonlinear function, and this linear function here. And when we have this situation, the thing we're going to do is set the equations equal to one another and then solve. So the two equations we're given are y equals 4 times the absolute value of x plus 1 minus 2. And the second equation we're given is y equals negative x plus 9. All right. Now, because we know that both of these equations are equal to y, and because we know if we're looking for the solution to this system, the y and the x in both of these equations are the same number, we can say, all right, if this is equal to y and this is equal to y, that means this is equal to this, right? Because the y's are the same. And we're saying y has this value here, but it has this value here. These two must be identical to one another. And so we're going to rewrite these two equations as just that, equal to one another. We're going to say 4 times the absolute value of x plus 1 minus 2 is equal to negative x plus 9. And now we're going to go ahead and we're going to solve. So the easiest thing to do right away is just to add 2 to everything. That's going to cancel out. We're left with 4 times the absolute value of x plus 1 is equal to, over on the right side, we got this negative x, and 9 plus 2 equals 11. Okay? Now, we're going to deal with that 4 outside of the absolute value sign, and the easiest way to do that, the only way to do that, is to divide. Can't distribute because it's not parentheses, so division is what we have to do. And so we end up with the absolute value of x plus 1 is equal to negative 1/4 x plus 11 over 4. Which is not the nicest thing to look at, but we don't have to worry too much about it right now. What we can do from here is, now that we've got this absolute value statement by itself, we're going to go ahead and we're going to consider our possibilities. We're going to consider the definition of absolute value. If we're saying the absolute value of x plus 1 is negative 1/4 x plus 11 over 4, then we can say one of two things. X plus 1 is equal to negative 1/4 x plus 11 over 4. Or we could say x plus 1 is equal to negative 1/4 x plus 11 over 4. Okay? What's happening there is, just like before, where I'm considering the positive and the negative version of whatever numbers I'm looking at, I'm doing the same thing here. It's just that it's an expression instead of a number value. And we're allowed to do that. It's okay. We're still going to get the solution we're looking for. It just takes a little more work. So I'm going to go ahead and start with the left. And I'm going to make my life a little easier on the left by multiplying everything by 4. Really and truly, that probably should be something we do for both of these. But let's hold off on the right side just because we have that negative distribution to worry about first. So over here, we do all the multiplication. We're going to end up with 4 times x, 4x. 4 times 1, 4. 4 times negative 1/4 is just going to be negative x, negative 1x. And 4 times 11 over 4 is going to get me positive 11. Okay? If I want to continue solving from here, the next thing I would do is I would add x to both sides. I would end up with 5x plus 4 is equal to 11. I would go ahead and I would subtract 4 from both sides. I would end up with 5x is equal to 7. And I would finish off there with my division. And I would end up with x is equal to 7 over 5. Which I believe is the same thing as like 1 2/5, so 1.4. Okay. Over here on the right, let's go ahead and let's handle this distribution first. Negative 1/4 x is just positive 1/4 x. And negative 11 over 4 is just that, 11 over 4, but making negative. All right. Now we're going to go ahead. We're going to use that same multiplication trick to make our life a little bit easier. Multiply everything by 4. Do the distribution, you end up with 4x plus 4 is equal to x minus 11. Now we go ahead and we solve. We're going to subtract x from both sides. We end up with 3x. Let me use that in white this time. Plus 4 equals negative 11. We subtract 4 from both sides. We end up with 3x equals negative 15. We divide everything by 3, and we end up with x equals -5. So those are our two solutions. Okay. Let's go ahead and let's write those. And so you're picking positive 1.4, so D, and -5, so B. All these others, let's get rid of them. And our last one of the main set of problems here, we got Emery, who can use no more than 178 beads making necklaces and bracelets. It says each bracelet uses 10 beads, while each necklace uses 16 beads. Emery must make at least 5 bracelets and 6 necklaces. It says, let X represent the number of bracelets and Y represent the number of necklaces Emery makes. We need to select all the inequalities that represent the constraints for the situation. Constraints is what that word says. So, let's go ahead and start with our totals. We know that 178 is a total. Number 18. And that she can use no more than that, right? So we need to say less than or equal to. We know that 5 and 6 are totals. Totals representing the number of each she needs to make, bracelets and necklaces. And if we put those together, we know 11 is also a total. 11 meaning the total number of accessories. The problem tells us she needs to make at least 5 bracelets and at least 6 necklaces. At least tells us we're using a greater than or equal to because she's okay with making more, but she needs at least that many. Okay? And so she needs at least 11 accessories in total, right? So now let's figure out how our variables and our coefficients are working. We know that in terms of bracelets, she uses 10 beads, and they told us to use X to represent the number of bracelets, so that should say 10X. And for the number 5, she needs to make at least 5 bracelets, so that's going to be X, which needs to be greater than 5. For the necklaces, we know she uses 16 beads. So 16. And they tell us in the question Y represents necklaces. So 10X plus 16Y can be no more than 178. And Y has to be at least 6. So that means the combination of bracelets and necklaces needs to be at least 11. Okay? And so those are going to be the inequalities that represent what we're looking at here. Now, we see a match for what we wrote in A, B, C. D is problematic because the sign is going the wrong way. It says that we can have less than 11, which isn't true based on what we wrote. E and F have their signs going the wrong way. And the problem with G is it has the wrong total. So A, B, and C are our answers there. And we're done with our review sheet. Now, before I let you go, there's one other thing I want to talk about, which is a couple of questions that don't show up on here. I want to talk very briefly about arithmetic sequences and our piecewise functions. Okay? We'll do arithmetic sequences first. So it says, on Gabriella's first birthday, her parents gave her a $50 savings account. On every birthday after, her parents added to the account, increasing the amount they deposited by 25 each year. Let's say that we wanted to write the arithmetic recursive and explicit rules for this scenario. So we should recognize is that the first term is here in the $50, and that our common difference is $25 each year, right? So A1 equals 50. D equals 25. So that means for our recursive rule, we'd write the following. 50 when n equals 1, and a n minus 1 plus 25 for when n is greater than 1. Right? Now for our explicit rule, we're going to write whatever term we want to find is going to be equal to the first term, which is 50, plus the common difference, which is 25, times n minus 1. Okay? And now let's say we were challenged to find the 18th birthday. Right? How much money she's going to have in her account on her 18th birthday. Instead of using the recursive rule, which is only really helpful if we want to find the next term in a sequence, we want to use the explicit rule. So, I'm going to say A18 is going to be equal to 50 plus 25 times 18 minus 1. And that 18 tells us what we're plugging in for n. And now we're just going to go ahead. We're going to simplify. 50 plus 25 times 19. It's going to equal 50 plus 25 times 10 is 250. 25 times 20 is 500. And then take away 25, so we should have with 475. Let me double check that real quick. Yep, looking right. So 475. And 50 plus 475 gets us 525. Okay, so that tells us that we're looking at $525 in her bank account on the 18th birthday.